Hello everyone. Today we will be discussing the USACO problem, Circular Barn. This is from the February 2016 contest and has both a silver and gold version, with the only difference between the problems being the bound on n. Therefore, we will discuss both problems during this video. If you want, you can go ahead and pause the video right now and look up this problem yourself to read and understand it. When you are ready, come back to the video. So the gist of the problem is that you were given a circular barn with a bunch of cows lined up at different spots or different doors. Each cow can enter through the respective door they're lined up in front of, and then they move clockwise around the barn and they choose to settle in one given spot. I think it's best described with this sample test case. So I went ahead and drew the sample test case right here. The idea is that this is for n equals 10, there are 10 different spots. And for a given spot, say this one, the number written at the spot is how many cows are waiting outside this given spot. So here there is one cow waiting. And once a cow enters, they can move any number of steps clockwise around the barn until they choose a room that they like, and then they're going to settle in that room. And so, for example, this cow could walk 1, 2, 3, 4, 5 rooms clockwise after entering the barn, and they can stop here. So you want all the cows to enter the barn, move to their respective locations, and when you're done, there should be one cow and exactly one cow at each and every spot. And the sum of all the array values, the sum of all of these numbers is guaranteed to sum up to n in the problem. So once you've done all of that, once you distributed your cows across the different rooms, you want to add up the squared distance of how much each cow moves. So for example, if this cow right here moves the aforementioned 5 spots, right? This is moving 5 spots, 1, 2, 3, 4, 5. Then we add 5 squared to our answer. If some cow here that moves 2 more, not 2, because they can't possibly be in the same room. Let's say this cow right here that moves 1 spot over here. Then you add 1 squared to the answer. And you just add the square distances for each and every cow. And now the question is, how do we distribute the cows, one to each room, such that the square distance, or the sum of the square disti for all the different cows, is minimized? And so in this example, we can do something like this, maybe 2. From here, we're going to have 1 cow move here, and we're going to have 1 cow move there. Then next, in this room, this cow is just going to immediately stay here after it enters. This cow is going to have 1 stay here, there are 2 of them, and the other one is going to move to this room. At this spot, the cows are going to move to here and there respectively. At this spot, they're going to move to here and there respectively. And finally, this 1 cow over here is going to move all the way over here. And let me just also make this 1 arrow to make it consistent. It's going to be 1 arrow, like so. And so if we add up all the disti, we get, this is, I'll start from here. So we get 1 squared plus 2 squared plus, this will be 0 squared plus 1 squared. This should be 0 squared because this cow also doesn't move anywhere. This is 1 squared. This is 1 squared right here. That's going to be 2 squared. This is going to be 2 squared. That's 3 squared. And finally, this last cow is going to move 3 squared. And if we sum up all these values, we get, what is this? 18, 20, let's see, 18, 20, 26, 28, 4, yeah, you're going to get 33. You sum up all these values, you get 33. And indeed, the answer to this sample test case is 33. And if you do have different cases, you're going to find out that you can't get a better answer than this. You can't get a better answer than 33. And so now the question becomes, well, how do we get to this answer of 33? How do we decide that we're going to do it this way? Well, if you look at the way I distributed the cows, it looks like I'm doing some sort of greedy strategy. right? It kind of looks like every time I'm choosing a cow, I move it like I move it the minimum distance possible. Except like it's, right, like for example, from here, for example, from this spot, I move the cows to this location and that location. So I kind of moved in the minimum distance possible. And then here, I would do here and there, but this is already occupied, so I can't do there. I have to instead do here and there. So it looks like I'm doing some sort of greedy strategy. But it's not exactly greedy either, because these cows should have stopped here and there if I was doing a greedy strategy. But instead, I didn't. Instead, instead I moved them 2 spaces out, right? This is a little strange. And in fact, I think you can probably tell that the reason why I moved 2 spaces out was because if I only moved 1 space out, if I only put them here and there, then this spot would be a 0, and then I would have to waste extra distance moving some cow from like all the way over here to that 0 spot, which is clearly not very efficient. And so there are a couple observations we can make after like playing around this for a while. One of the observations we can make is that say we have a cow here, and it's going to move some distance. Let me make this smaller. So we're gonna have, let's say we have a cow here, a cow there. We have some destination there and there. And let's say we have 2 options. We can either move a cow. So let's say these are like 2 spots where cows can enter, right? These are 2 spots where a cow is waiting behind the door, and these are 2 spots where that we want to fill, right? This is some sort of general case. And we'll notice that we kind of have 2 options. Either A, we insert this cow here, and we're going to insert that cow there, or B, we're going to have this cow walk all the way over here, and we're only going to have this cow walk over here. These are kind of the 2 ways that we can fill these 2 cows into these 2 spots. Maybe I should mark this as cow, cow, and these 2 will be spots. And so, which of these 2 is more optimal? Well, we can kind of just compute and see which of these 2 scenarios is more optimal. If we call this distance A, call that distance B, and call this C, then we'll notice that in scenario 1, our total distance is going to be this here, A plus B squared, plus this here, from here to there is going to be B plus C squared, right? In the other scenario, it will be A plus B plus C squared, right? Because let me use a different color, the green. In the other scenario, it will be A plus B plus C squared plus, from there to there will be B squared. Now the question is, well, which one is bigger? And if you expand out both of these terms, just kind of like do some math and expand it out, you'll find that this is always the more optimal option, right? Like, well, if you expand it out, what you're going to find is that this is always less than or equal to this. So it's never going to be optimal to take the green scenario, to do the green scenario of moving a given cow like farther and then moving some later cow closer. It's always going to be more optimal to drop off a cow as early as possible, to have a cow move have each cow move as minimal distance as possible from in the clockwise direction. This is always going to be a better scenario. And so that's kind of what we're going to do. We're going to just have each cow, we're going to take each cow, right? We're just going to keep essentially we're going to start at some point in the circle, and then as we come around the circle, each time we encounter a set of cows waiting outside the door, we add into our total, and each time we encounter a spot, we have to drop off 1 cow. So if you think about it, right, in this example right here, I could have started from here instead. And what would happen is I would kind of just walk in this direction around here. Each time I encounter like a spot, like say a 2, I add 2 cows to kind of like my set or my group of cows. And at each spot, I also have to drop off one cow. And I'm going to choose to drop off the cow who was collected the earliest, who entered the group the earliest, because that's what my greedy strategy tells me here. And the only question left is, where do we start? Because here's the thing, right? We know for a fact that there must exist some spot that we can start at such that we can follow the greedy strategy. So in this example here, I started here, which is actually not an optimal spot. If I start here, then I can't follow the greedy strategy and get it to work out. But if you do this case out again, starting from this point instead, you're going to find that the greedy strategy does end up working. And so the question is, where do we start? And well, in the silver version of the problem, as you can see here, in the silver version of the problem, n is only 1,000. So we can just naively try every single spot on the circle and ask, hey, if we start here, will we be able to distribute all the cows across the circle, right? So you can just try every single spot. You can try here, there, so on and so forth, and you can take the best answer out of all of them. However, for the gold version of the problem, right here, you can see for the gold version of the problem, n is up to 100,000. So we wouldn't be able to try all the spots anymore. So like in the silver version of the problem, if we try every single spot, each starting spot, then it takes O of n time to simulate the process, and there are O of n different starting spots, so it becomes O of n squared. In this case, if we do O of n squared with n equals 100,000, we're going to get time limit to exceed that. It's going to take too long, so we have to come up with a better way of doing that. And so, yeah, so we've already solved this. Basically, what happened here is we already solved the silver version of the problem. We just need to now figure out how to solve the gold version. And just to clarify, in case you're wondering why this works, we know for a fact that some valid starting spot will always work. Like there's always going to be some spot where we can initiate the greedy strategy and have it work out. And the way to prove that is, well, we just think about it. If there's no valid starting spot where we can fill in all the different, where we can make it work out by following the greedy strategy, then there's always going to be some spot that's left empty. There's always going to be some spot where we're not going to have enough cows when we get there. And that kind of contradicts the original requirement that the sum of all the array values, the sum of all the cows waiting outside the doors is n. Because that just means we don't have enough cows to begin with. Like we're always going to have enough cows, so there's always some valid starting spot. Or we can't possibly not fill in all the spots. So that's why that works. Now, even if you're not in the gold division, if you're in the silver division, I still recommend you stick around, because the way we solve the gold problem is not that complicated. It doesn't really require any sort of higher level algorithm. It just requires a pretty slick insight, in my opinion. And so the insight we're going to make here is that we can kind of write out this whole greedy strategy thing as like an equation, kind of, or a formula. So let's say we're going to visit C1, C2, C3, ... up to Cn. Well, we just need to make sure that at each and every given spot, when we get to that spot, we have enough cows left in the reserves so that we're not like stuck, right? Like in this example right here, the reason why we can't stop here is because by the time we get to this spot, then per the greedy strategy, we won't have enough cows in the reserves to fill that spot in. And so we can kind of write this out as an equation, right? So at this first given spot, we add C1 to our total, and we're going to drop off one cow. At this next spot, we're going to add C1, we're also going to add C2, and we dropped off one here, we dropped off one there, minus 2. Next spot, you can probably guess, it's going to be C1 plus C2 plus C3, because we started here, we visited all 3 spots, and we've collected all the cows there, and we've dropped off a total of 3 cows at these given locations. In general, at the ith spot, we're going to have, if we started from, assuming that we start from C1, we're going to have the sum of from 1, should not use I, I'm going to use K. At the kth spot, we will have the sum of from 1 to k of ci minus k. And we need to make sure that this quantity is greater than or equal to 0, it's never negative, for all k. And it's pretty easy to see why this statement corresponds to what we're talking about, right? At each given spot, we've collected the sum of all the c's or all the array values that we've come across, right? Those are all the cows that we've added to our group. And at each step, we also drop off one cow. And so this value just needs to be non-negative for each possible spot that we reach. Because if it's negative, that means there's a greater demand for, or rather, we're not going to have enough cows when we get to the spot if it's negative. And you can, if you're still confused, just kind of like look at it for a second. Maybe think about what I've already said, do some examples, and just notice that this kind of corresponds to what I was talking about earlier. This condition needs to be true. And so let's just go ahead and you can kind of notice, right, that from this, when we're transitioning, okay, let's just call this f of I for sake of simplicity. Notice that when we transition from f of I to f of I plus 1, it's pretty simple, right? We add the ci plus 1th value, and we subtract 1 because we have to drop off a cow. And that is equal to f of I plus 1. And that's how we're going to compute the next one based on the previous one. If you want to perhaps graph the value of f, right? I'm just going to draw a graph here, right? Then the x-axis is going to represent the I value. The y-axis is going to represent the f value. And let's say our thing is not valid, right? I don't know. Let's say I'm just going to extend this graph a little bit so we can. Yeah. So let's just say your things at each step, right? We're gonna start at 0, and let's say it looks something like this, right? Each time you move, you add some amount. Maybe you add some amount. You maybe deplete some amount. I don't know. Maybe you deplete some amount. Deplete, and maybe at some point it drops to negative, right? So this doesn't work out. Something like that, who knows? But the important part is that we know for a fact that it would eventually, this is a very bad graph, but we know for a fact that eventually it must end at 0. We know for a fact that when I becomes n, I'm interchanging I and k, that's not good, okay? So at this point, just like, sorry, here it's just i's to k that I was talking about earlier. Yeah, but you kind of notice that it must end at 0, right? Because we know for a fact that the sum of all ci is equal to n. That's how we know that we can even fill in all the spots in the first place. And so the sum of all n minus n, which will be how many we dropped off, must equal 0. So our graph must end at 0 when I becomes n. The sum of all ci from 1 to n minus n must equal 0. And so, yeah, we'll see that maybe our graph dips negative. We don't want a graph to dip negative. We want to start at some spot such that our graph never dips negative. Let's take this spot, for example, right? We're just going to take some spot that's like very low, maybe here. And what do you think happens? What do you think happens if we start at this spot instead? I'll give you a minute to think about this. Not a minute, but just if you want, you can pause the video and think about it, because this is quite important. What happens if we start right after the spots that is most negative? What's going to happen is our graph is going to look very similar. So if we start here, you can think of it kind of like a rotation, right? But like if you start here, that means we're going to end there. So this is going to get raised up to here. This point's going to be up here, right? This is also going to get raised up to, say, there. What's going to happen is that the shape of our graph, something like that. Just imagine that just use your imagination and imagine that if we start here, this wraps around. right? I just like, because like we would just be shifting it over. We have a different starting spot, so we would just redefine the eyes per se, or we would just consider the graph as wrapping around. But you can convince yourself that the graph's shape is still going to be the same. At each spot, we still add ci plus 1 minus 1. From when we transition from our function from one value to the next, we're still adding by the same constant value. So our shape is still the same. The only thing that changes is where we started. And if we choose to start here, then we're going to end at the most negative spot. And because we know that by definition, the last spot we visit must be equal to 0, its f value must equal 0, the entire graph just gets shifted up because the shape is still the same. It still gets shifted up. You can convince yourself this is true. If you don't believe me, just pause and think about it. But it's very true. The graph just gets shifted up. And now we know for a fact that no value in the graph is going to be negative because you've already chosen the most negative point in the graph, the lowest point. And we've shifted that above or up to the x-axis. And so now no part of the graph is below the x-axis. And so that's going to be our solution. We're going to assume that we start at like initially at 1. We're going to basically form the graph. We're going to find the lowest point in the graph. And we're going to rotate our array or change our starting point such that we start right after the lowest point. And now when we start there, we know for a fact that our process is going to work. We're going to find a good answer. We know that we're never going to reach a point where we run out of cows. And so it's going to take O of n time to kind of like form this graph and find the minimum spot. And then it's going to take another O of n time to rerun the algorithm after we've shifted our starting point. So overall, our complexity will be O of n, which is enough to solve the gold version of this problem. All right, so let's go ahead and implement this solution now. So I'm just go ahead and just gonna write some stuff that I need for every program. This is just the usual. I'm going to read from our file cbarn.in and cbarn.out. Awesome. I can make a note here. This is it's fine. Okay. And what we're gonna read in, n, and then we're going to read in c, which is how many cows are waiting outside each door. Let's just go ahead and make c a global array. I'm gonna make a size 100,000 so that it also works for the goal problem. Just gathering input. So what's next? Well, we have to form the graph, right? So let's just assume we start at position 1 and see how the graph goes. So we're going to have a running sum. And we're also going to have the lowest, right? This will be the lowest point. So we're going to store the lowest value. This will be infinity at first. And we're going to store the lowest index, which is where the lowest value occurs. Right now it will be -1 because it doesn't exist yet. We haven't started yet. So now, for each value, we're going to add to our total C of I. We're going to subtract 1 because we must drop off 1 cow. So this is going to be part 1, finding the lowest point in our graph. We're just going to go ahead, we're going to find the lowest point. And then, if sum is smaller than the value of the current lowest point, now the value becomes equal to the sum, and the lowest index becomes equal to this spot, I. So what's part 2? Part 2 is we're going to start at index directly after lowest point. And so one way we could do this in C++ is we can just rotate our array. So we can rotate it such that our starting point is some other index in the array. That can be done. So we're going to say start index is equal to lowest index plus 1, so right after. But if the lowest point is, actually the lowest point can never possibly be n, because by definition that point must be equal to 0. Well, I guess for posterity's sake, yeah, we can just do that. It's fine. So we can plus 1. If it becomes equal to n, then it wraps around, Now we're going to go ahead and just rotate the entire array. And now we're going to run our algorithm again. This time we're going to keep track of the actual answer. Now we are going to need long for this, for each spot. So here's how we can do this. We need to keep track of the cows that we currently have in our reserve, and we have to drop off the lowest one, or the one that with the lowest index, because that's like equivalent to the one that we picked up first, right? We want to drop off cows that we got as early as possible. And so the way I'm going to do this is I'm going to keep an array that's going to maintain the count of how many cows I have that's originated from the ith index for all the indices from 0 to n. Or I guess 0 to n minus 1. Yeah. Here's what's going to happen. I'm also going to have a pointer. J is going to represent, maybe not J, it's not a descriptive name. I'm literally going to call it pointer. It's going to initially start from 0, right? And so here's what's going to happen. Yeah. So I'm going to go ahead and I'm going to increase. We're going to say that at the ith position, we just gained ci new cows. And now while count of pointer is equal to 0, right? So while we don't have enough cows from the ith position, we're going to bump pointer forward. So we want to remember, we want to find the earliest possible spot where we have a cow available, because then we want to take from the earliest spot, because that's what our greedy strategy dictates. Once we found our earliest spot, we're going to deduct 1 cow. I'm going to drop off 1 cow from that spot. And then we're going to update our answer with the square distance from this spot I, the current spot where we're dropping off a cow, and where the cow originates from, where they originally entered the barn. That's what we're going to add to our answer. It's going to be a square. And at the very end, we're going to print our answer. And we're just going to see if this works. So to see if this works, I have already created a file called cbarn.in with the sample input. So let's see if this works. It ran, but let's see if it generates the right answer. 33. Awesome. So now let's just go ahead and see if this is correct. So this is the Siilver version of the problem. I'm going to submit there first. It should work for both versions. Awesome, it works. Now let's see if it works for the gold version of the problem. This is the gold version with n equals 100,000. This should still work because it's O of n complexity. And it works. Awesome. So yeah, that's going to be circular barn. That's how you solve the problem. So I guess the gist of this problem is kind of observing that a greedy strategy works, maybe thinking about a specific scenario where you're considering two different cows. How do we decide what order to process the cows in, or who to drop off where? That's how we motivate our greedy strategy, is by considering a simple scenario like this. And then to get to the O of n solution, we kind of just thought about like what exactly we have to actually make sure is true in our problem. In this case, we notice that this condition of maintaining this like sum of c sub I minus k being greater than or equal to 0, that's the condition that we notice we must be true in order for our spot to be a good starting spot. And that's where we kind of motivate this idea of like kind of like maybe seeing a graph and then once we draw the graph, noticing that we can shift this lowest point up to keep the graph positive. So it's all different steps that we have to go through in order to get to the solution. And I know it's not obvious at first, but if you do enough practice problems, these things will naturally come to you. So that's it. Thank you for watching. Bye-bye.